Guess we'll go ahead and get started. Welcome to FayettePy. My name is Chrissy. That's Casey. He's the founder of FayettePy and then brought me on as a co-organizer last year. He is also the CEO of Lofty Labs, the place where you are right now. I do not work for Lofty. I think that's the number one question I get here. I work for a company that's based in Indiana, and they also run the largest tech meetup in the state of Indiana, IndiePy. I was going to wear my scarf. I have an IndiePy scarf now.
Scarf?
I do.
We need scarves, although it's not that cold here.
No, not really. So I'm kind of getting some ideas from them of the things that we can do with FayettePy. So first of all, to start off, each time we have a talk, we'll also do some beginner tips. So if you are completely new to Python, or even if you are experienced with Python, you may learn something. Actually, there's something I learned in here today, which one of my coworkers was surprised I didn't know, and then also my boss didn't know it either. So I want to talk about different methods that are available on lists and also using dir. So let's make a list called numbers. So a list with numbers 1 through 4. I'll make that nice and big so everyone can see. So if you run dir on and pass it numbers, it's going to give you a list of the different methods, functions that are available on it. So you see a lot of these here that have 2 underscores before, 2 after. Those are called dunder methods. For the most part, you probably won't need to do much with those. Those aren't necessarily things that you will be calling in your own code. The ones that you're mostly going to be looking at are the last ones here that don't have the dunders. So you have like append, count, extend, index, insert, pop, remove, reverse, and sort. So if we try to do numbers.reverse, it's going to tell you that is a built-in method. And when you get something like that, that means you need to call it. So numbers.reverse with open and close parentheses. And it doesn't seem like it did anything, but if we look at numbers again, just type in numbers, print it out. I'm just in a Python interpreter here. And sorry, I guess I am using Python 2.7, but everything's going to be the same. But you can see now numbers, that list has been reversed, 4, 3, 2, 1. So now something else that we can do with dir at this point is if you just call dir and don't pass it anything, this is what I learned. It's going to show you everything that is available in the current context. So like the last one there is numbers. That's the variable that I created. So if you're working like in a file or you've made a bunch of different variables and you don't know exactly what's available, you can just type in dir and see what you have. So you can see there's my numbers variable that I created. All right, let's see what else we can do with this. So another one is sort. So if I do numbers.sort, just like reverse, it looks like it didn't do anything, but I can check it and see now once again everything is back to 1, 2, 3, 4. Let's say let's try append and see what that does. Okay, now I get another error. It says append takes exactly 1 argument and 0 givens. That means it's expecting you to pass something to it that you're going to do with it. Now let's say you don't know exactly what the append method does. We can do do dir of numbers.append, and we can see what is available on that one. Doesn't look like there's too much helpful here, but what you can do, if you look at numbers.append dunder doc, that's going to show us the doc string from that method. And so it says it appends an object to the end. So we will do numbers.append, pass it a 5. And look at numbers again, and it has added a 5 onto the end of it. If you want to delete something on the list, this one's a little bit different. You would say del and the space numbers, and then you can pass it an index. So we talked about list slicing another time. So in this case, I'm not grabbing number 2, I am grabbing the item that is at the index 2. So if I delete that one and look at numbers again, you can see I took out 3 because the counting starts at 0, so 0, 1, 2 is actually number 3 is what was removed. Another one, let me see, we've lost all of our functions, so if you need to check again, you can do a dir of numbers. Let's see, another one we can look at is pop. So numbers dot pop. So now this one's a little bit different. It gave us 5, which we know is the last one in there. If we look at numbers again, it has removed it from the list. So this can be helpful if you want to pop the last item off of a list and then assign it to a variable and do something with that further on. Let's see what else we have. Another one is numbers.count. Now see, this is another one that's taking, it's expecting an argument to be passed to it. So let's look at that doc string on this one. And it tells us it's going to return the number of occurrences of a value. Okay. Let's change numbers a little bit first. You can see what I did there. I just took the list, multiplied itself by 3 times, and so it's just repeating a few times. So if we do numbers.count, check how many times the number 4 appears, it appears 3 times. So those are your beginner tips.
Sweet. Curiously missing is push. You can pop from a list. But if you want to push to it, what do you insert at
yeah, you can.
At 0, insert at.
Yeah, I think I must have forgotten to put that one down. But yeah, that is another one with insert.
No, it's not. I mean, it's not a. Yeah.
But yeah, with insert, you can specify the index of where it will show up in the list.
It's just interesting that pop and push were such a core concept for lists or arrays in like computer science, and they implemented a pop method but not a push. It's part of the Zen of Python, I guess. Like there should be one and only one way to do it. And we already had insert at 0, so that's the way to do it.
Probably append has the same push, right? So maybe that's why they might have that.
Yeah, so
Maybe.
cool. All right, thanks, Chrissy.
Yep.
Hey, Chrissy,
Yes.
is the help built-in available?
I have built-ins.
It may be in there. If you were to type help, open quotes, and then numbers, and then close it, what would that? Yeah.
Oh, nice.
That's magic. It's not technically a built-in.
Yes, then once you get there, it looks like it's just Vim command. So if you click J, that's going to be down, or down arrow would do that too. Q to quit.
Yeah, more. That's interesting. That's what you get that in IPython when you type like question mark or double question mark. I always thought that was an IPython thing. I had no idea that was built into the Python. I've never seen that.
I think that's why people, and I've experienced, I've done it once or twice, if I haven't put good doc strings in, people complain.
Yeah.
Because some people are still relying on that.
Totally.
Which I was like, I thought everyone was using IPython or like a BPython or some kind of like flavor of a new interpreter by now, but no, people still like that built-in.
That's pretty cool. That was a beginner tip on its own. Or not beginner tip. I've been doing this for 12 years and I didn't know that was there.
Obscure Python facts.
Well, cool. Thanks, Chrissy, for some beginner tips. All right, welcome everybody. This talk is intended to be interactive, which is, if you've ever given a talk, you know that's potentially a disaster. So bear with me, but thanks for coming out. So let me preface this with, there's a lot of math in here. I don't know about you guys, but I enjoyed math. But let me preface that with, I went to college, I got a C in Cal 1, and I dropped stats. And that's the extent of my actual post-secondary math. So as much as I enjoy math, I'm not incredibly great at it. We're going to talk about some and hopefully explain it. But the crux of this talk could be 3 lines of code. And I could say, here you go, use these 3 lines of code, and now you can do predictive analytics on certain cases. But I think it's really important to talk about the math. If some of you are better at math than me, then forgive me because I might mess it up. But I promise that there's a practical component to this, and so follow with me. Also, if the math part is too much for you, I promise we'll tie it all together by the end of it. So, Chrissy already mentioned, but my name's Kinsey. I'm the CEO of Lofty Labs, which is where you are. We're a software development consultancy that specializes in building web applications with Python and Django, kind of our tools of choice. I'm also co-host. Isn't this fun, Alan? Do you put your name on this ever? I'm doing it now. It's in my Twitter bio. I'm a co-host of a podcast.
Yeah, I'm adding it to my email.
Yeah. Do it right now because Alan's on there with us. So there's kind of 4 of us from our core team here at Lofty and some guests that come with us that are all co-hosting a podcast called Friday Afternoon Deploy. So episodes come out on Fridays. It is a very laid-back kind of look at dev culture and the stuff that we're working on. It is not necessarily safe for work, depending on where you work. So it's super laid-back. But we do get into technical stuff. We also talk about, nostalgia and video games and that sort of thing. But episodes come out on Fridays. There's a link there. It's Friday@hirelofty.com. We're on iTunes, Spotify. We're 16 weeks into it. Episode 16 comes out Friday, tomorrow. And so we've been having a really good time with it. You can find me on Twitter, though I never update there except to spam you with links from our podcast and occasional articles that our company posts. And this is our company, hirelofty.com, and of course the website for our podcast. That's me. Predictive analytics. Anybody work with predictive analytics on a daily basis as part of your job? Okay, a couple of you. You guys are the ones that don't kill me if I mess up math. We do it a lot too, and I want to kind of pre-qualify. This is the formal definition, right? But predictive analytics is a broad field, a bunch of different techniques, but basically any way of taking data and analyzing what happened in the past and inferring what might happen in the future. That is predictive analytics. Anybody work day-to-day with machine learning in their jobs? That's interesting. Okay, so not everyone that's doing predictive analytics is working with machine learning, which is cool because that's kind of the point of this talk. Because what I'm going to show you today is not necessarily machine learning, but so much of machine learning that's happening these days is in the world of doing some sort of predictive analysis. But machine learning, if you're not familiar with it, is basically what we used to call statistics run on a computer, right? But now it's its own thing, or really data science is maybe statistics on computers. But the important thing from this definition is the premise that algorithms can receive input data and predict an output while updating their outputs as new information becomes available. So they're trainable. They're trained and they learn, right? We're not really going to talk about machine learning today, although we're talking about simple regressions, linear regressions. Linear regressions are a component of tons of different types of machine learning algorithms. They're sort of a building block, but they're pretty powerful on their own. Simple linear regressions. Statistical method for summarizing and studying relationships between two continuous or quantitative variables. An independent variable and a dependent variable. We'll define those a little bit more if you're not familiar with those terms. But it's that two continuous variables is something that's really important to understand here. So we're talking about linear regressions. Linear being related to a line. That's what makes it linear. There are two kind of there's probably more than this, but if you're looking at linear types of functions, you can kind of think of two different groupings of them. Classification type linear functions and regression functions. We're talking about regressions today. And that's where that continuous variable comes into play. So classification is for discrete variables. A discrete variable is true or false, dog or cat or pony. A continuous variable is continuous. It's something in a continuum of numbers, right? So if this number gets this high, this number reacts in what kind of way? Those are continuous variables. So you can do things linearly with classifications, which is basically, fundamentally, can I draw a line in simplifying this down to just two-dimensional space, right? X and Y, two variables. Can I draw a line such that anything that falls on one side of the line is classified as one item, and anything that falls on the other side of the line is a different item? That's a classification algorithm. That is what kind of movies will you like on Netflix, right? people were also interested in. Those are classification problems. We're going to talk about regressions, which is this. The idea is, can I plot a line that best fits my data such that I can use that line to make a reasonably good assumption about what that data is going to do in the future or what it might have done in the past. That is a regression. So that's kind of the difference there. So that kind of frames up the sort of problems that you would solve. And it all comes down to this guy who took geometry in high school. Does everybody remember the slope-intercept form of a line? Y equals mx plus b. M is the slope. It is the both the direction and steepness of your line. B is the y-intercept, which is the point at which that line crosses the y-axis. Right? How high up the y-axis does it cross? That is the formula for it's the function definition, if you will, for a line. And all of this is kind of based on that premise. The most common form of linear regression uses something called the least squares method, and I knew that before I started writing this talk, but I didn't know actually what the least squares method was, because, spoiler alert, there's one function call that does this for you in pandas, and we're going to talk about it today. But I was like, I want to understand the math, and so I started looking up the least squares method, and I couldn't find a damn method anywhere until finally someone said, hey, it's really the least squares criterion, which makes a whole lot more sense. It's not really a method. It's a definition of criteria that would satisfy the least squares method. And that criterion is hopefully on this slide. I'll give you an illustration, though, of how it's calculated. Okay, so here is a scatter plot of data. Right, these are points, just good old coordinate pairs of x and y. This would be 0, 0, right? And you've got your two axes. So these are your data points. This is hypothetically a regression line. This is what we want to calculate and what we use to make predictions. This is a line that best fits this data. And how do we define best fits? Well, the least squares criterion says you've got these little segments here. And these segments are called the residual. And the least squares criterion says the line which best fits this data is the line in which the sum of the squares of the residuals, so this distance squared plus this distance squared plus this distance squared, the sum of the squares of the residuals is minimized. Whatever line has the smallest sum of squares is the line of best fit for this data. And like kind of fun fact, why do we square it? Well, it amplifies error, right? You could just add up the distance, but if you square it, you exponentially increase the visibility of error. And also, it's a mathematical shortcut for absolute value, right? Because some of these are positive and some of them are negative, but if you square them, they're always positive, okay? So it makes for easy math. So you sum the squares, and that is your line of best fit. So from that graph, I didn't have markers on the axes, but like based on the ratio of those residuals, the sum of squares would have been 26. And you could kind of brute force or Monte Carlo this problem and fit different lines and calculate the sum of squares. Fortunately, calculus, yes, but I mean really statistics has covered us here. For a simple line, linear regression, this can be calculated in order one time. There is a formula for it if you do some calculations on the data set and identify some statistical values. I thought about explaining those values, and then I realized there was a sweet cheat code to this process, and so now I'm going to step away, and we're going to watch a video briefly that explains it. So I'll let Khan Academy, which is awesome, kind of explain to you the rationale and show you the sort of intuition of how this formula is arrived. So you don't have to take my word for it, or his word for it, but you can understand kind of where that comes from. So let me pull that guy up. And I hope everyone's able to hear this pretty well. We do have subtitles on there, though. Oh, but I don't have audio.
Data, and we calculated the correlation coefficient. And just as a bit of a review, we have the formula here, and it looks a bit intimidating, but in that video we saw all it is an average of the product of the z-scores for each of those pairs. And as we said, if r is equal to 1, you have a perfect positive correlation. If r is equal to -1, you have a perfect negative correlation. And if r is equal to 0, you don't have a correlation. But for this particular bivariate data set, we got an r of 0.946, which means we have a fairly strong positive correlation. What we're going to do on this video is build on this notion and actually come up with the equation for the least squares line that tries to fit these points. So before I do that, let's just visualize some of the statistics that we have here for these data points. We clearly have the 4 data points plotted, but let's plot the statistics for x. So the sample mean and the sample standard deviation for x are here in red. And actually, let me box these off in red so that you know that's what is going on here. So the sample mean for x, and it's easy to calculate, 1 plus 2 plus 2 plus 3 divided by 4 is 8 divided by 4, which is 2. So we have x equals 2 right over here. And then this is one sample standard deviation above the mean. This is one sample standard deviation below the mean. And then we can do the same thing for the y variables. So the mean is 3. And this is one sample standard deviation for y above the mean, and this is one sample standard deviation for y below the mean. And visualizing these means, especially their intersection, and also their standard deviations, will help us build an intuition for the equation of the least squares line. So generally speaking, the equation for any line is going to be y is equal to mx plus b, where this is the slope and this is the y-intercept. For the regression line, we'll put a little hat over it. So this, you would literally say y hat. This tells you that this is a regression line that we're trying to fit to these points. First, what is going to be the slope? Well, the slope is going to be r times the ratio between the sample standard deviation in the y direction over the sample standard deviation in the x direction. This might not seem intuitive at first, but we'll talk about it in a few seconds, and hopefully it'll make a lot more sense. But the next thing we need to know is, all right, if we can calculate our slope, how do we calculate our y-intercept? Well, like you first learned in Algebra 1, you can calculate the y-intercept if you already know the slope by saying, well, what point is definitely going to be on my line? And for a least squares regression line, you're definitely going to have the point sample mean of x, comma, sample mean of y. So you're definitely going to go through that point. So before I even calculate for this particular example, where in previous videos we calculated the r to be 0.946, or roughly equal to that, let's just think about what's going on. So our least squares line is definitely going to go through that point. Now if r were 1, if we had a perfect positive correlation, then our slope would be the standard deviation of y over the standard deviation of x. So if you were to start at this point, and if you were to run your standard deviation of x and rise your standard deviation of y, well, with a perfect positive correlation, your line would look like this. And that makes a lot of sense, because you're looking at your spread of y over your spread of x. If r were equal to 1, this would be your slope, standard deviation of y over standard deviation of x. That has parallels to when you first learn about slope. Change in y over change in x. Here you're seeing you could say the average spread in y over the average spread in x. And this would be the case when r is 1. So let me write that down. This would be the case if r is equal to 1. What if r were equal to -1? It would look like this. That would be our line if we had a perfect negative correlation. Now what if r were 0? Then your slope would be 0. And then your line would just be this line. Y is equal to the mean of y. So you would just go through that right over there. But now let's think about this scenario. In this scenario, our r is 0.946. So we have a fairly strong correlation. This is pretty close to 1. And so if you were to take 0.946 and multiply it by this ratio, if you were to move forward in x by the standard deviation in x, for this case, how much would you move up in y? Well, you would move up r times the standard deviation of y. And as we said, if r was 1, you would get all the way up to this perfect correlation line. But here it's 0.946. So you would get up about 95% of the way to that. And so our line, without even looking at the equation, is going to look something like this, which we can see is a pretty good fit for those points. I'm not proving it here in this video. But now that we have an intuition for these things, hopefully you appreciate this isn't just coming out of nowhere and it's some strange formula. It actually makes intuitive sense. Let's calculate it for this particular set of data. M is going to be equal to R, 0.946, times the sample standard deviation of Y, 2.160, over the sample standard deviation of X, 0.816. We can get our calculator out to calculate that. So we have 0.946 times 2.160 divided by 0.816. It gets us to 2.50. Let's just round to the nearest hundredth for simplicity here. So this is approximately equal to 2.50. And so how do we figure out the y-intercept? Well, remember, we go through this point. So we're going to have 2.50 times our x mean. So our x mean is 2 times 2. Remember, this right over here is our x mean. Plus b is going to be equal to our y mean. Our y mean, we see right over here, is 3. And so what do we get? We get 3 is equal to 5 plus b. 5 plus b. And so what is b? Well, if you subtract 5 from both sides, you get b is equal to -2. And so there you have it. The equation for our regression line. We deserve a little bit of a drum roll here. We would say y hat, the hat tells us that this is the equation for a regression line, is equal to 2.50 times x minus 2. And we are done.
Cool. So if any of that, like, you didn't follow perfectly, that's okay. There's no expectation anywhere that you need to be able to calculate that just, offhand. Please come out of there. But it's worth noting how that's done. So there is a formula for it. You're not going to have to necessarily calculate an R value. And there's other videos in that series. Khan Academy is awesome, by the way, if you don't ever use it. Like, they post most of their stuff on YouTube. And there's other stuff in that series that shows how they got to the R value and things like that. But the point is that you can take a data set and you can calculate an R value. You can calculate standard deviation on both axes. You can calculate your means. And from that, order one calculation of what your regression line is. So we're going to use code. We're not going to do it data science from scratch style where we implement functions that calculate all that stuff. We're going to use NumPy and Pandas, which have all that stuff built directly into it and rolled up into a nice function for us. But I wanted the math to kind of be understood there and understand where we're coming from to kind of visualize it. And they just did a way better job of explaining it than I ever could. So we're done with slides. We're ready for code. Everybody cool with that? Excellent. Can everybody read the code? Is this pretty legible? Is that good? In the back? Cool. Alex, good? All right. So, and I can put this up somewhere where you guys can access it. It's a Python notebook if you haven't seen it yet. So we've got an active Python interpreter and we can run this code. We're using NumPy and Pandas. NumPy is the low-level library for all kinds of math, statistics, and matrix math specifically in Python. And then Pandas is a really much nicer developer interface for interacting with it. And they have this thing called a data frame in Pandas, which is an awesome way to deal with tabular columnar table data. So think of it as multi-dimensional lists, right? And they have cool stuff. And then the matplotlib thing, or plotlib, is just so we can graph some of this stuff. That's specific to the notebook. So we're going to create some random data. I'm going to take this up just like a tiny notch. At the very least, for the people on YouTube, maybe that's more readable. We're going to make some random data. All right, so we're going to pull up the random library. We're going to create 20 points in the range of -10 to 10 on both the x and y axis. So we're going to disperse, a 20 by 20 grid, basically, of 20 random points. So we'll do that. There's our points. This is fun because those are different points than the last time I ran it. It's totally random, pseudo-random, okay? So those are our points, just like you saw in the bivariate data set in that last example. We have 4 points, we've got 20. And now we're going to use pandas to create a data frame from the variables. So this is a list of 2 tuples, or it could be a list of lists that length 2, right? But these are x and y, and we've got a list of them. We pass this list of tuples in, and we say, hey, the first item in each tuple, that's column x. The second item in each tuple is column y. So we're turning this into a columnar data store where we've got an x column and a y column. That lets us do cool stuff with pandas and NumPy, like give me the sample mean of x. You can just tell it to average a column. It does it. Super awesome. So we have made a data frame, and we're also going to plot it. So we're going to create the data frame. This is going to print the data frame out, but we're actually going to plot it so we can visualize what the data looks like. So we're just plotting x and y as x and y, and we're doing a scatter plot. Control Enter. Did I skip a step? Yes, I did. I didn't run the first block. Cool. So there's our data frame. There are 20 data points. So this is what we already saw. But you see what I mean when I say columnar, right? It's like an Excel spreadsheet. You've got multiple columns for each row. This is just the number of the row, our x value and our y value. And visually, that's what that looks like. So about as random as you expected, maybe. The fun thing about random data and why it's pseudo-random, and I think this shows up maybe a little bit if you pay attention, is it's not that random. There's at least a little bit of signal in it, right? So now, based on what we know, we can create a regression line for this. And you don't have to do any of the math that we just saw. NumPy has a function called polyfit. This is a polynomial fit, okay? This will do a linear, a line. It'll do a linear regression or a linear fit. It will also do other polynomials. So if you remember polynomials, the idea being like slope-intercept for a linear, what is that, a monomial? Binomial would be mx plus b, but like you can have a trinomial or a quadratic formula, which might be, slope 1 times x squared plus slope 2 times x plus b, and so on and so forth. This will actually do more than linear. Let's focus on linear for now. We'll talk about why. But what we're doing is, hey, do a polynomial fit. This is my x column. This is my y column. This is my independent variable, and this is my dependent variable. And the 1 here is the order of the polynomial. So this is a line. We're going to do 1x value for it. And this is like a method factory. What it creates is a little function for us. Or I'm sorry, the next thing, poly1d is a method factory. What we actually got here was just this. It's a NumPy array. It's like a list, but it's NumPy, so it's got some extra stuff on it. NumPy array with 2 values. Anybody know what the 2 values are? Any guesses?
Slope and coefficient.
Slope and y-intercept, right? So this is your slope. So that's it. We've calculated the regression line. We have everything that we need to know. The slope in this particular set of data is 0.02, and the y-intercept is -0.4. That is our equation. It's just a numeric representation of the coefficients. Now it's the poly1d method that we're going to use next. That is like, think of it like a method factory. It'll take those coefficients and it will create a function for you, and you can use that function to calculate things with this polynomial. So we'll do it, and what we're going to do is those constants. So this is what we get from the polyfit. This is this array here, and we're going to call poly1d and pass them in, and we're going to get this this method. And when you print it out, it actually shows you what you expect: slope x minus the y-intercept, or plus the y-intercept, which happens to be negative. And that's it. With this, we can make predictions. we can use this line, that line that goes through the data, and we can say for some point on the x-axis in the future that wasn't in our data set, I'd say in the future if it's time series, but further down the axis that wasn't in our data set, anything that appears on that line, so if we put the x value into this function, the y value we get out is on that line, that is a prediction that is dead center in the standard deviation, right? And if you want to predict a range, you can add the standard deviation to either end of it and say it's somewhere between this and this. But this is as accurate as we can get based on our data set and based on how strong that R value was, the correlation. Some prediction. And I see that I spelled prediction wrong, so can't use regressions for that. Yeah, so we're going to use this function, and remember all of our values were between -10 and 10, but given that distribution of data, what would the regression tell us that an x value of 14, what would that be on the y-axis? And the answer is -0.12. Okay? That's based on that regression line. Now, the regression line is only as useful as that R value. How strong is the correlation? Remember when he said when the R value is 0, you basically get a flat line? Because if the R value if there's not a strong correlation, the best you can do is average all your Y values, right? You have an independent variable like time, and you have values that are changing over time. If there's no correlation in them, the best you can do is, what's the average that's happened over time? Is that kind of intuitive to everybody? Based on the last 30 days, this is the average of what we've seen, so that's the best we know. But if there's a stronger correlation, if there's a trend in that data, you can do better than picking the average. You can look at the way the data is trending, and that's what the regression line tells us. So I'll stop beating that horse. Also, this function does more than just letting you, pass a single value into it, and that shows up in just a minute. So it's more than just a function. I will tell you now that this took me way too long to figure out using pandas. So matplotlib is actually a little bit more straightforward. When all your data is in a pandas data frame, plotting your scatter plot like we had and actually drawing the regression line on it was not intuitive. We do this thing where we plot the line and we capture that in a variable. What we have to do is basically add a column to our data frames. Remember we had X and Y? Then what we do is we add another column. I'm calling it regression. And the value of that column is our polynomial function. This is our line of best fit, our regression line. And we pass in the X column of the data frame. So not only can you pass in one value for X and get Y, if you pass in a list or an array, it will return an array of everything plotted across that line. So basically, we walk down our x-axis and we have our scatter plot. Remember that, right? Walk down our x-axis and we plot each y value in the line, and that builds the line. We capture that in the variable. We run our scatter plot again. I have no idea what AX stands for, but it's how to layer multiple plots on top of one another. Blah, blah, blah. There we go. So that's like the weakest correlation yet in the random data, which is awesome. Almost a flat line, right? So remember what he said? If your slope is 0, or not if your slope is 0, but if your R value is 0, which would translate to, it's a coefficient, so your slope would be 0, weak correlation. So what can we predict with this? Almost nothing. Why doesn't it fit the data well? Because it's random data, right? So trick question, what can we predict? Well, if the data weren't random, you would see a much stronger correlation. But obviously, we're pretty close to just saying our best prediction is the average of Y, right? Which was between -10 and 10. Spoiler, is 0, right? So there's almost no correlation here. Funnily, people tell you that it's pseudo-random numbers. A couple times that I've run this in preparing for the talk, there actually was more slope in this line, which indicates that the numbers aren't truly random. There actually is some signal in it, but this time, that's damn near random. You can roll some D&D on that. So, okay. So that's all the code. I'll give the code sample so you guys can find it and use it. Can't predict much with that. Let's try some real data. So this is real data. Captured out in the real world. Our independent variable is time. This is time series data. You can see it starts last month. It goes all the way back to 2011. Pretty sparse data set. There's years between some of this data. And all the Y values are somewhere between 10,000 and 72,000. And if you look really, really close, you might notice something just right off the bat looking at the data. And if you don't see it, I'll tell you what it is. The number goes up over time. It always goes up. As time increases, the number goes up. So you can already kind of look at that and say, okay, there's a correlation in this data. Over my independent variable, there's a trend in this data. We're going to build a data frame from it. This is just some quick math to take these date times and convert them to Unix timestamps, because Pandas doesn't do great work with actual date time values. So that just lets us get it numeric, right? Because it's a continuous variable. And then we're going to plot a scatter plot. So look at that. So this is some real data. You can look at that and say, does anybody feel that there is a slightly stronger correlation in this data than maybe the last one that was totally random, right? You would be correct. You can look at this and say, there is definitely a linear correlation, like I see a line forming. It's not perfectly linear, but it's very strong, okay? And we can calculate a regression line for it. So same thing, right? Instead of, x and y, we have our date value and the y value. We're going to do an order 1 polynomial. So we're doing a line. We're going to calculate the regression and plot. Same code from before, but using our new data set. That is our regression line. So much more tightly fit to the data. Does anybody who doesn't work for Lofty Labs that I haven't spoiled this for want to guess as to what maybe this data is? Coffee machine? Or coffee machine? Coffee? Yeah, we got 80,000 pounds over the last 100 years. That's probably, I mean, anecdotal, but that might be close, right?
What's the unit of measuring?
Oh, well, that would give it away. That would give it away, I think. So no units here, so I'm cheating.
I would have a guess that it's like stars on a specific repo for like a framework.
Stars for a repo? No, that's a good one though. No, check this out. Hang on, I think I have something supporting it here. So I pulled this out of my glove box. This is the maintenance records for my car since I bought it in 2011, and this is my car's mileage over time. So I kind of had an idea a while back for a pet project because I really like taking care of my car. As you can see, I kept all my maintenance records. I wanted to do something with it for a long time, and I knew that there was some way to do some AI with it and things like that. And like most people who come to Lofty Labs, our company, saying, we need AI and machine learning. No, you just need a linear regression, okay? And so that's what this is. Like what we can do with this is we can look at as my actual mileage over time, but we can use that regression line, right? If this is time, to kind of predict off the chart, extrapolate that line, keep it going further, and say, what might my car's mileage be somewhere down the road based on this regression, okay? And it works. And I've built a little app around it. We'll get into it. We'll pull it up right now. I made a mistake, though, a critical error in this talk. First of all, it's on a free Heroku dyno, so we have to wait 30 seconds for it to spin up. But I was supposed to take a picture of my car's mileage before I walked in here to show how accurate it is. So I can't tell you. I know that it was relatively good, but it wasn't perfect. It's like predicting within maybe 1,000 miles or something like that. So I have two cars. We have the family car, the Renegade, and we have my Scion, my TC. That's the one that we were looking at the data for. And this is how I've used the regression in the real world. This is my actual mileage log, right? So these are the actual miles known. Some of these I logged manually. Some of them are associated with maintenance. And I have a schedule in here. I run full synthetic, low viscosity oil in my car, so I do an oil change every 10,000 miles. I know my last oil change was at 70,592 miles, so I expect to need an oil change at 80,592 miles. Based on this trend line, right, we take the independent variable of time, which would be the x value I pass into that polynomial function, and say, what's today's date? And based on that, the y value is 73,321. I think I'm at 72.9. I'm pretty close to that, 72.9. So it's accurate within about 500 miles, which is pretty awesome for a couple of reasons. One, this is taking in my car's mileage data going back to 2011, and my driving habits have not been that consistent. So you kind of have to look at your data. Like this is an important part of data science. You can't just throw algorithms and functions at data. You need to understand the domain. You need to understand the nuances. And particularly when you're not using machine learning is really good at, I have 40 variables in this equation, help me tune them all simultaneously. Okay, linear regression, we're talking about two variables, x and y, simple linear regression. So you, the data scientist, the engineer, the explorer, the person who knows it, you have to figure out what, there are other variables actually in this data set that you don't have numbers for. And for me, it's, car mileage, it's my commute to work. It's my lifestyle driving habits, right? Which have changed over time. Simultaneously, we can do a different type of prediction with it. So this is where it thinks my mileage is. We can flip those variables and run a regression, and we can because there's such a strong correlation, this wouldn't work with all data sets, but because that's almost a line, right? We can flip the variables and say, I tend to drive the same amount every day. So based on what we know there, I know at 80,592 exactly is when I'm going to need an oil change. That's 10,000 miles from my last one. So we flip the variables. We do the same thing. On my x-axis, at 80,592 miles, what is the y value? And I'm going to need an oil change. This is how I don't drive my car enough. You can tell I live 2 miles from the office. I'm not predicted to need an oil change until April 24th, 2020. So the only thing about my app here that's falling apart is I didn't account for oil life outside of mileage. Like, I need to get my oil changed before then, or I need to drive more or something like that. And the same thing with tire rotation, just on a different schedule. So I'll need to rotate my tires, because I like to do that every 5,000 miles on June 1st of this year. So this is like just a practical application of linear regression. Does that kind of make sense to everybody? And you can see with this code of how we're doing it, it's a little more complex where we've put it all together here. But basically, once you get your data loaded into a data frame, and all that code's for plotting it, it's really just using polyfit on your values and this poly1d, and you have this function. You pass an independent variable into it, it gives you the corresponding dependent variable. If I wanted to make this like a little more statistically rigored, if this were something that you needed to deliver this information with caveats, this should probably be arranged. This is the point on the regression line. I could make this say somewhere between one standard deviation of y in one direction and one standard deviation in the other direction, and say it's going to be somewhere between, I actually haven't looked at what the standard deviation is, but maybe since it's that far out, I'm guessing it might be like a 3-month range, right, in both directions. I don't really know until I calculate it. But I don't drive that much, apparently, is what I learned doing it. But yeah, so this is kind of an example. So I mentioned, you need to know your data. You need to know how these formulas and functions, what the other variables might be to be accurate with it. So here's something that's really interesting. I said my driving habits have changed over time. If you kind of look at how this regression line fits, I don't drive the same amount year over year. This was way back in 2011. The line between these two is much steeper than the regression, right? And here it starts to turn, and then it turns, and then it goes really far less steep than the regression. And I can tell you the explanation between every data point, because from when I bought the car, I lived in Hot Springs, and I drove to downtown Little Rock every day. It's 60 miles commute one way, and I was dating a girl that lived in Dallas, so I went down there once a month. It's a lot of miles. Put 20,000 miles on my car in the first 6 months that I owned it, as you can see. But at some point, I took a job working from home in Hot Springs. So that was cool. Stopped driving to work all those miles every day, and the steepness goes down. Still dating the girl in Dallas, though, so didn't come all the way down. And then all the way up here, the girl I was dating in Dallas moved to Arkansas, and so then my driving went way down. But I stopped working from home. I started working from here, and it's probably about 5 miles from my house. So you can see that my mileage has tapered off over time. Also, a couple months ago, we bought a family car, and that's the car we take on road trips now. And so my poor car just gets seriously 5 miles a day, and I don't get an oil change for a year. But yeah, so that's the fit of it. Now, you could get really tricky with this polyfit. we're doing linear regressions right now. That's the whole point of this talk, which is basically over. We'll open it up to questions shortly. But you can do other things that aren't linear. We can do quadratics, right? We can try and fit this curve, and that's the function for that. I don't know as well. I don't know how it's calculated. It wasn't in that Khan Academy video, but thank you, NumPy. Makes it very easy. I changed that to 2, and we're going to calculate an order 2 polynomial now. Check that shit out. That's accurate, right? Like, look at how well the regression line fits. Okay? Now, it's really tempting for me to go change my app, right? To say like, but it's going to predict so much accurately, which given the data I gave it, it will. Does anybody have a guess as to why that might be a bad idea? Overfitting, exactly. You hear about that a lot in machine learning, right? But this is the most simple form of overfitting. The reality is if you kind of remember what these graphs look like as you start adding more components to the polynomial, these curves start getting crazier and crazier. And the reality is I can go all the way up to 12, and at some point NumPy starts going like, okay, dude, you don't know math. Like, warning, there's no way this is accurate. You're doing a 15 nomial equation, and you only have 11 points in your data set. But oh man, it's accurate. It's from point to point. It predicted every single point accurately. The problem is that if I try and predict, and unfortunately I wish I had the code set up because I can't pass a date time, and I have to look up a Unix timestamp for it. But if we just try and ask it, hey, what's it look like next week? It's going to be like, oh, you need an oil change in the year 1492. It's going to be way off because this is just like zoomed way in on a very complex curve. That's what happens here and ends up fitting it. And I can give you maybe a way simpler illustration of it by going all the way back to this guy. The first time I increased the order of this polynomial. Okay, so this is a function that is something like m sub 2 x squared plus m sub 1 x plus b, as opposed to just mx plus b. Right. So this is a quadratic equation. Does anybody remember what it looks like when you graph a quadratic equation? What the graph looks like? Yep, it's parabola, right? So it's a parabola. It's like a normal distribution. It's a type of parabola. It goes up, then it comes down. And so we know for sure, if we know that that's what this type of equation looks like, if I use this, we know our data domain. So if we didn't know what this data was, hey, maybe it's a distribution, right? Maybe this is like income distribution, which tends to actually fit a normal distribution curve till you get to the very top. Sorry. Or maybe it's something like demographics or gender or grades or something like that, IQ, things like that tend to fit a normal distribution. And hey, that's a perfectly reasonable assumption to make given that data. It is not at all a perfectly reasonable assumption to make with my car's mileage, because if we say, hey, let's try fitting a parabola to it, look, it might work now, but if we look far enough in the future and we know the shape of parabola, that regression is going to tell you that if I wait long enough, my car's mileage will go down. And there's just no way that that's going to happen, right? So you have to be really careful with how you use this. The reason why people talk a lot about linear regression is it's a much safer way to do predictions. You might be able to fit a line to this that fits the data you know well, but the more you fit it, the more like dangerous the risk of overfitting is. And like you can see the real risk there is I could say, hey, what's it look like 10 years from now? It may well say you've only got 40,000 miles in your car. We know that's not true, right? So yeah, that's kind of what I wanted to show you guys today. From the portion of the talk that is how to apply this in software, I gave you a practical example of what it looks like. Happy if anyone's interested to crack open the source code. This is just a Django app. It's that same code I just showed you in the notebook, except we're doing it in a Django view, right? We just have a function that we say, what's today's date? Cool. Here's your mileage. So there it is. You guys have any? I'll open it up to questions.
Because the better data to put in the linear test would be how many miles you drive in a year. Yeah, it could be either how many miles you drive in a year, or one of the things that could be done. I think what
what I plan to do with this, I'm actually going to use this out. I just built it a couple weeks ago. The actual plan is to keep it linear. I actually prefer to filter the data in this data set down to the last 6 months. If I did it with here, I'd be plotting a line between 2 points because I only have 2 mileage logs. But the plan is to actually start logging my mileage weekly. It kicks me an SMS message in the mornings, like once a week, that says, hey, real quick, send back your mileage. And so hopefully I get it when I get to work and I look at my mileage gauge that I put it in and start getting more points. And if I look at it within 6 months, it's more likely to be fitted to my recent driving habits than over time. I was shocked, and Alan and some of the guys on our team, when I was building this, I kept running out of my office. I was like, it's really close. Like, I keep keying in more. Like, I started with my oldest mileage log, and I'm 5 years ago, and I'm like, it's within 5,000 miles of my current mileage. It's amazing. But it would get a lot more accurate if it were my current mileage. And I just don't have the data yet to show it. But yeah, so something about, it's either what you suggested, right, is like fitting this with kind of some realistic expectations of what your current mileage is. Or limiting the data that you're doing analysis on to something that eliminates variables. And for this, it would be by narrowing the data set, we'd be eliminating variables in my driving habits somewhat, just life changes and things like that. One of the other things, I had something, and I've lost my train of thought now, which is too bad, but maybe it'll come back to me. But yeah, there's kind of some other ways to kind of improve this by kind of knowing what risks there are for overfitting the data. Anybody else?
Is the Django app open source?
It's not. I'll put it on GitHub. I need to scrub the database out of it. Not that I'm like super protective of leaking my mileage history in my car. There's way worse data to find on me. But yeah, I need to scrub some stuff out of it. I can put it up. We actually we do have somewhere out there, it rarely gets updated, but we do have a FayettePy GitHub organization that you're all, I think everything's on, it's public, but I think there's a link somewhere on the meetup page in the discussion group or something. So I'll try and put that there along with the Python notebook that has this code in it.
I was going to say, probably, I know you can even host your notebook as stat HTML.
Yeah, there's a couple of different services that do that. We can put that up there. It'd be a good way to interact with it. It's awesome. You just run it. The other thing I was going to say, Christy, is that, oh no, I'm getting old. It went away again. It just occurred to me that I shouldn't do that. I put myself on the spot. Yeah, sorry. Did you see it? Did you see me feeling it, like slipping away? Like oh no! But I just saw it.
Like trying to catch a ball that's just too high.
Yeah. Just right out of my hands. Yeah. Oh well, I'm also getting old and I don't care. Anybody have any other thoughts or like applications for this? Again, like, this doesn't work for classification. This isn't the type of algorithm that will tell you if a picture is a cat or a dog. That's classification. But this can tell you, continuous variables. You're comparing two sets of real numbers, and one needs to be independent. One needs to not have any outside influence, right? That's what it is. So one variable needs to be dependent on the other, and it just so happens that mileage in a car is dependent on time, at least in some extent, unless you don't drive the car. Okay, I got it now. It came back to me. You talked about saying how many miles you drive a year. So that's one of the things you can do is kind of look at, you're looking at a local average. You're looking at the average over the past year. And when I originally started to do this, I actually wasn't going for linear regressions. I was just going to do it all based on average. I was going to do exactly that without a regression at all and say, well, how many miles do I average in a day? We'll just take all the days and we'll take all the miles and we'll divide the miles by the days and there we go, right? And that would give you more or less what we have here because I'm going to the beginning of time, my driving habits have changed. This is pretty well reflecting the average, more or less. But each one of these is kind of, you can think each point on this line is sort of an instantaneous look at the average at that moment, right? Because if I look here, and I look at all this data, and I plot the average of this data, that's actually a horizontal line right here, right? And so I look at my average per day, so it'd be that horizontal line times the number of days, which might get me there. But if you think about data that's trending, and anything you do with an average, this just came up on a client project, is a horizontal line with no slope. An average will work really well if your data is unchanging, if you can reasonably assume that the average is continuing. But if there's a trend in your data, and you plot an average and you say, well, let's just pick whatever the average was, you're going to come up short or maybe come up high if your data is trending in the opposite direction. So you can think of this as just a step beyond using averages. Think of it kind of like, there's probably a mathematician that would skewer me because I'm not saying something mathematically honest, but I like to think of it as an average that is taking account for the trend in your data. Kevin, I think you know math more than me. Is that relatively reasonable?
Yeah, well, it is. It is just if you were taking the average but updating every time.
Yeah.
Another thing.
Kind of like an instantaneous average. This is the
Right.
average at this moment based on what we knew, but now we know this, and the average went up, right?
If you had multiple variables, then it would make it a lot more complicated. But
Right. So this is also, again, two variable. This is a simple linear regression. There is a type of linear regression with a line called a complex linear regression or a multivariable linear regression. You can do this with lots of variables. Fortunately for us, I don't even want to get into the math of how that works because I didn't even, like I said, I dropped stats, which was still very two-dimensional. Yay! Pandas and NumPy, you just pass more columns into it and it knows how to do a multiple regression. But I think, someone that is closer to this than me can verify, but the more variables, the even more careful you need to be about the types of predictions you're making. You need to sanitize your data. There's always outliers that can skew things, and you just have more variables to think about of how I might be overfitting this data or what might be influencing this outcome. You just have to have even deeper knowledge of the domain.
yeah, it cuts both ways because if you leave out variables that are extremely important to making a prediction, then it messes up what variables, the coefficients that you're getting on the variables that are in there are not accurately representing what they should.
Yeah.
Because they're having to pick up some of this other thing. But
because you're essentially, like in a way, kind of overfitted to data that's missing this other data.
right,
So like, given this data set, your coefficients are this.
you're saying miles is really important. Well, what about where I live?
Right.
Or,
Yeah. So like other variables that could make for a much more interesting machine learning problem. Like this is never a product that I'm going to take the world by storm with because someone's going to write neural networks that account in like, well, where do you live and how are you feeling that day and all of these other things, But that's perfectly a good example of like how far do I live from work? How far do I live from my kid's school? Do I have kids? How many kids? How many schools? These are all variables in my actual driving habits. But looking at it from just a simple regression, it simplifies the variables and it will be less accurate than knowing them all, but it will be way more accurate than kind of guessing at multiple variables, right? And that's why this is a really safe way to do statistical predictions because you run no risk of like overfitting on a bunch of complex variables. It just won't be as accurate, like you said, if you start missing variables that are really integral to this. They're highly dependent on the independent variable.
Yeah.
How did you say we could get this from you?
I'll post it to the comments for this event on Meetup. I don't know exactly where I'm going to put it, either GitHub or one of these hosted notebook services, but we'll get it up there. And so if you just go back to the event page for today, in the next couple of days, I'll post this code as well as we're going to put the video on YouTube. So if you want to go back and look at it, and my slides and all that, I'll try and bundle it all up. Cool. Okay. Well, thank you guys for coming. Thanks for listening to my deal. And I'll do like one last totally shameless plug for the podcast. New episode comes out 9 o'clock tomorrow morning. Friday afternoon deploy, friday.hirelofty.com. So
You said you are on iTunes?
we're on iTunes, Spotify, Google Play, Stitcher, and hopefully everywhere you can possibly find a podcast. We worked really hard to simulcast. So, and you can download RSS feed and episodes directly from our website. Cool. All right, thanks everybody. Feel free to hang out and mingle and chat, and thanks for coming out. And do we have something scheduled for next month? Do we know what the event
Next
is?
month we're going to do the project showcase.
Project
So,
Showcase.
If you have anything that you've been working on that's pretty cool, bring your laptop.
It's
I don't
here
know.
too, right?
I set that on the event.
I think we should. Yeah, I think that's a good spot.
I think this would be a good space for it.
So we'll set up different stations. If you got something cool you're working on, bring a laptop. Feel free to come set it up. And the idea will be just everyone kind of mingles around and goes from. If you don't have anything to show off, come see all the stuff that people are showing off. And so we'll just hang out and play some music and look at code and talk shop. So that'll be third Thursday next month. Cool. Thanks everybody.